Hello class, and welcome to today's lecture. My name is Professor Circumference, and today we'll be discussing several important key concepts in the exciting world of physics. We're just waiting on our demonstrator before we begin. Here he is. Better late than never. Here's my understudy, Mr. Dextrose, who will be using his balls of differing size to guide you through the lecture. Let's jump straight in by discussing the observer effect using a model of heavy hydrogen. Mr. Dextrose will now assemble the atom using one proton, one neutron and one electron. The observer effect, often mistaken with Heisenberg's uncertainty principle, tells us that in quantum physics, the physics of the incredibly small, when we observe something, we cannot directly ascertain where exactly it is at any one moment. This is because when we look at something, we have affected it and it changes its behaviour. If Mr. Dextrose wants to observe the electron, he is interacting with it and therefore cannot tell exactly what it is doing. Indeed, the physical phenomenon you are all observing right now is similar to that of dark matter, in which we can feel its presence and see its effects, but we currently have no way to physically observe it. Moving on, let's discuss the elusive yet abundant neutrinos. If Mr. Dextrose takes an atom of helium-3, you will see that the neutrinos have such little interactivity with regular everyday matter that they simply whiz on by at nearly the speed of light. In fact, they are so incredibly uninteractive that if you took a whole light year of lead, you just might have a chance of stopping one. How are our audience doing, Mr. Dextrose? Still awake? I hope they're taking notes. They're going to need them for the quiz at the end of class today. So far today, Mr. Dextrose's particles have all been out of proportion. Mr. Dextrose, will you please reveal your appropriately sized balls? In reality, the relative size of the proton and neutron to that of the electron is much more like this. The sizes of the balls here show the differences in mass of the particles, with the electron roughly a 1/1800th of the mass of the proton or neutron. And if the overall size of the atom is this room, defined by the orbit of the electron, the proton and neutron would occupy a space the size of a petit pois at its centre. And now, ladies and gentlemen, time for our final demonstration. Electrons are the reason for the high reactivity of the element sodium, and for its explosive reaction with simple compounds such as water and even air. Mr. Dextrose, if you would like to prepare the electron launcher and the sodium sample. Don't forget your safety glasses. As the sodium metal hits the water, its free electrons in its outer shell are quickly used in the reaction, creating hydrogen gas, which produces a wonderful visual effect. Are you ready, Mr. Dextrose? Thank you everybody for listening today, but don't leave right away, as Mr. Dextrose will be handing out your examination papers shortly. Good luck everyone!